the debates and battles between different scientists about the validity of these measurements, but there was a reading or a signature indicating phosphine in this cloud layer. So now a scientist put together a reaction that could take place to generate a product like phosphine, and it requires a lot of energy in that sort of environment. It's 8 protons are needed to react with phosphoric acid. But after doing the research, I was ultimately swayed in favor of Mars, and that's due to its unique feature in that it might have a habitable environment in its subsurface, which hasn't been investigated very well or thoroughly at all. You kind of want to see a straight line going all the way down to the bottom right little peak there. But that's actually not the case. If you look really closely, you can see it actually curves off halfway down and then forms a ridge there. And that's clearly a natural formation of a ridge. The sulfur monoxide can result in diatomic sulfur in S2, or maybe even S3, S4, S5, etc. And this can all coalesce to make a membrane, a sulfur-based membrane, driving the reaction zone within the membrane, this sulfur-based membrane. This reaction zone is where energy transfer will be taking place, electrons moving around, reactions taking place, a form of metabolism. And there's even sodium chloride on the moon that could stabilize some of these reactions that are taking place and driving the activity of this life form, this organism-like being. We have our top 3 candidates that we've assessed so far in Venus, Mars, and Io. In this video, I want to kind of recap where we left off in the Investigating Life series. We've already talked about life on Earth. We've gone through several planets and moons within our own solar system. And then I want to update you guys on my model for predicting life on other planets. It is a constantly changing, updating, and iterative process, so it'll change with time. And so the values or the probabilities I assign to the various planets and moons I've done so far will change by the end of the series. The 2 things I want to talk about in this video are the model itself. I have a new presentation I want to unveil for it, and then I wanted to just summarize quickly what we've done so far with the different planets in our solar system and moons that I've analyzed so far. So just to begin, my model, I am changing the presentation, the way it looks, from before it was just a product operator times P and then the weighting symbol. I want to change the P to a D, so instead of calling it penalties, we're now going to call it drivers. I think this is just more coherent with the language I use, because sometimes when the penalty increased, that actually led to an increase in the possibility of life on that object. Whereas if we call it a driver, it just makes more sense to say if that increases, yes, that's driving the likelihood that increased likelihood of life existing there. So no longer is it a P or penalties, we're calling it a D for drivers. Everything else is staying the same. And then I'll come out with a new video, hopefully pretty soon here, that breaks down pressure, similarly how I broke down temperature. And then the other thing to talk about is just recapping the various different solar system objects we've already looked at, and that led with Mercury, which we identified as a very unlikely place to have life. The probability we were able to churn out was roughly 0 due to the extreme temperature fluctuations. No way an organism of any kind could adapt to that sort of fluctuation in temperature, let alone the radiation, the lack of atmosphere, and the chemical composition on that planet, especially with its proximity to the sun. So roughly 0 for Mercury, and then we moved into Venus, and we actually arrived at a fairly high percentage compared to the other objects we've looked at 1.2%, and this would be in the cloud layer region of Venus. This region has a lot of interesting characteristics in terms of temperature and pressure, as well as its chemical composition that could be an invitation for life to arise there. The question is whether or not it could suspend itself in its fluid-like dynamics, given it's basically just going to have to float in this atmosphere. The next planet we looked at was Mars. We quickly looked at the image of that structure that looked like a civilization-made object or station or location. Kind of broke down why I don't think that's the case. But there is a 0.38% based on my model for life on the planet, and it would be in the underground region of that planet. It would be under the surface in caverns potentially, which haven't been analyzed or probed at all so far by all of the rovers and different technology we've sent there to analyze the planet. Then we moved into Jupiter, which has a pretty low probability at 0.056%. The planet is mostly helium and hydrogen. These aren't great elements to drive life if they're the only thing that exists there. The extreme pressure makes it an unlikely candidate for life to arise. However, its moons could be much more interesting. The only moon we've looked at so far is Io, roughly a 0.216% probability of life there, and that is because we were able to imagine a scenario where a sulfur-based life form could potentially come into existence. And it was fun to explore that and break it down, which I did already in a previous video. So that's kind of where we're at. We're going to continue to work through the solar system. Jupiter, moons, Saturn's moons, Uranus, and maybe Pluto, and then that'll probably wrap up the solar system. And then we can move to extrasolar bodies and systems outside, exoplanets beyond our solar system, and that will be very exciting too. So that was the recap I had for us, and I'll see you in the next video.